Can you see it?
Yes.
Medina, experiments with exponential sums over the binary field.
Thank you. Good morning. Well, we know Don is a great mathematician. He's also a great teacher, and he's great with his students. He's also a great postdoc. He has a great influence on me, and I want to thank you for that. Well, my talk will be about exponential sums over the binary field. So I will start with some definitions. The first one is the definition of a Boolean function. So what the thing that we will do is we'll take f to be the binary field, so it's the field of 2 elements. And a function is called a Boolean function if you go for the n vector space to the ground plane. Okay? So that's what a Boolean function is. Boolean function has a lot of applications in cryptography. They are used, for example, for the creation of strings cipher, stuff like that. The one that I will be concerned here are symmetric ones. Now, the exponential sum associated to a Boolean function is defined by this. So what you do is you take all the elements in the vector space and you take one raised to the value of the function. That's what the exponential sum is. It's also known as the Fourier transform of the element of the function. Sorry. Now, the subject can be studied from the point of view of complexity theory or from the algebraic point of view. The one that I started studying was the algebraic point of view because I like evaluation. That's something that I got from my advisor. So I got that bug. And so we got a paper of that where we actually compute exact two divisibility for exponential sums. Basically what we did was to extend a method called the Moreno-Moreno covering method. That's basically what we did. But when my colleague gave me this sentence, I swear that I heard Doran in my brain saying, this is false. Because it doesn't mention experimental math. So it can be studied from the view of complexity theory or from the algebraic point of view. So no, this thing has to be studied from the experimental math point of view, and that's what I will present today. Basically, what I will present is a work in progress. It's not done yet. I mean, it's not finished yet. So some things that I will present probably are known. But basically what I want to do is get my hands dirty and understand the theory. This theory is new for me. So the first thing that we do is we take an elementary symmetric polynomial of degree k in n variable. So it's the sigma k that we have there. And for example, if n is equal to 4, k is equal to 3, this is the polynomial that we're talking about. And what we want to do is to compute the exponential sum associated to it. So the first thing that we did is to rewrite this exponential sum. Okay? So we define aj to be the set of all tuples with exactly j enters equal to 1. If that is the case, then this is what we need to compute. And in this case, the function evaluated at those vectors is a constant. It's actually given by this for every one of them. And since the cardinality of our set is that, then our exponential sum is this. Of course, the right-hand side is okay if n is less than k, the other one is not. But I will ignore that, and I will concentrate on this. Okay? So that's the object that now we'll study. Now there is here a very elementary congruence that you can observe. So if you let r to be the unique positive integer such that k is bound between these two powers of 2, then it's not hard to show that you actually have this. So if this number is odd, then so is this. And if the number is even, then it's that. So basically what you do is you observe the first 2 r elements, you check whether they are odd or even, and then you know that every single 2 to the r block, you will have that. So you have a periodicity here. because of that, so the thing that I just said, you just calculate which are the odd ones, and then basically what you do is you divide the sum in the following. You assume first that, well, you drop this, so you get this, and then you subtract twice the ones that are odd in order to get the congruence. This one is, we know it's in kindergarten, right? This is this. And then that one is now the object that I want to study. So I reduce everything to this. So these are the ones that we will study. So I will let an to be equal to this. This part here you can ignore. This is a consequence of a copy-paste. This was actually needed for the proof of a theorem, but we didn't need that. Okay, so this is the function. This is the sequence that I will study now. So a computer, please. So that's not what I will do. Now, basically, what I did is first I tried to know how much my computer knows before I just start putting big machinery on it. So the first thing to do is, well, the computer algebra system that I use is Mathematica. So using Mathematica, Mathematica has a function called find sequence function. I put it there. I put a bunch of values of the sequence, and it returned something, but I didn't like it. It was too obvious for me. It was like a different root or something humongous, but it was a different root. So the other thing that I did was, well, let's try to see if it satisfies the recurrence. In this case, a linear one. So I input this, a Mathematica problem. Now this means that an20 is equal to this. That's the meaning of that thing. So then this is for the index I equal to 0. If you put 1, the same one. And in fact, if you go from 0 to 3, you will get that recurrence. 4 minus 6, 4 is actually this. So the next step is to check another example. Now I move to r equal to 3. And j equal to 0 gives me this one. This is the same one for every single one of them, from 0 to 7. And in this case, so it looks like Mathematica is suggesting that we have the following recurrence. At this stage, right, we will try to prove it either by computer or by human brain. Doran will be disappointed because I did it with my brain.